Okay, this is written team problem set number 1, problem 4. A book is held against a vertical wall. The pushing force of the hand is horizontal, so it's towards the right. The mass of the book is 3.5 kilograms, and the coefficient of static friction between the book and the wall is 0.45. Question asks, what is the minimum pushing force provided by the hand to hold the book in place? Okay, so we're going to start by drawing a free body diagram of the book. So let's draw a dot to be the book. And what are the forces acting on it? Well, let's draw a little diagram over here to remind us of what's going on. There's the book, there's the wall. So there's going to be a normal force coming off the wall. So we'll draw that as acting towards the left. And there's going to be gravity acting down. We'll call that m times g, where m is the mass of the book. I guess so we'll say m equals 3.5 kilograms as being one of our knowns. Okay, sorry, skipping forward just a little bit. We have the pushing force from the hand is directed towards the right, so I've drawn that on the free body diagram as well. I'll call it F sub P, and it's a vector. The next force is going to have to be this, whatever force is holding the book upwards. So if there's no static friction, then the x components of the x forces, or forces with x components, are towards the right, the pushing force, and the normal force towards the left. So those have to be equal and opposite so that the book doesn't accelerate into the wall or off the wall. And then gravity is pulling down. So what static friction does is it prevents the object from slipping against the surface. Since gravity wants to pull the object down and the surface can't slip, the static friction force must act upwards. And so I've drawn it now in the free body diagram acting upwards. And for the book not to move, we have to have that the net force, or sum of all the forces, is equal to 0. So let's add them up. So sometimes I like to make a table where I have x and y as being the columns, and we can label things in the left column, and then every row corresponds to a force. So the first force, let's start with, is the normal force. We forgot to define the x, y coordinates, so let's do that up here. Let's call y as being positive up, and x as being positive towards the right. So the normal force is just going towards the left, so it has an x component, negative n, and we don't know it, so we're just going to leave it as n. It has a 0 y component. The next force is mg. We know that g is a downward vector, so it has 0 x component, and it's down, so it'll be negative y, since we defined y as being upwards. We know mass and we know g, so this is a known quantity. The pushing force towards the right, we actually are looking for that, trying to find the pushing force, so we'll call it Fp. X component is Fp, it's positive, and the y component is 0. And lastly, we've got static friction, so we're just going to call it F sub s. We know that it's got 0 x component because it's going straight up, and it's positive y component. So here we have the sum of the forces, which is equal to F net. Let's add all these up. So F net in the x direction is equal to negative n plus Fp, and F net in the y direction is equal to negative mg plus F sub s. Now it's in equilibrium, so we know that both components of the net force are going to be equal to 0. So from this x component equation, we've got 0 equals negative n plus F sub p. So the pushing force, which is what we need, is equal to the normal force. Okay, fine. We don't know the normal force yet. From the balancing the y, we've got 0 equals negative mg plus the static friction. So the static friction is equal to mg. Okay. So we also know about static friction that Fs max is equal to the coefficient of static friction times the normal force. And what we'll do is we'll say it's just about to slip, when the actual static friction is equal to Fs max. Okay, so N here is the normal force of the wall in the book, and we don't know it, and we don't care about it. What we want to find is this F sub p. So these are two independent equations. I'm going to use this y equation, solve out for n, and then plug it back up in here to get our pushing force. So let's solve this for n. We're going to set this equal to F sub s. Solving for n gives n equals F sub s divided by mu sub s. We know that F sub s equals mg, so it's mg divided by mu sub s. Now we can plug all of this into the x equation for the pushing force. We're going to get F pushing is equal to mg over mu sub s. We know all these numbers. 3.5 kilograms is an SI unit times 9.8 meters per second squared is an SI unit, and divided by the dimensionless coefficient of static friction, which was 0.45. Okay, so time to take out the calculator, and we got 3.5 times 9.8 divided by 0.45, so it's 76.2222. Looks like there's two significant digits in all this because of the 3.5 and the 0.45, so let's just take F pushing is equal to 76 newtons, and that's your minimum force. Put a box around the final answer.